Hey everyone. In this video, I'm going to talk about visualizing distributions in R. And we're going to jump right back into the survey that I introduced in our previous video, where we looked at survey data from 2011 in Afghanistan, where social scientists went to southern provinces in Afghanistan to ask people about their experiences in the civil war and their support for both the international security forces as well as the Taliban. And specifically, we will use these data to kind of showcase some of the basic plotting functions in R. And as we proceed throughout the semester, we will kind of refine those skills and talk a lot about data visualization in R, because R, one of the great features of R is that it has very powerful capabilities when it comes to data visualization. And so we'll practice those skills a lot going forward. Okay. So the first category of plot that I want to show you is a bar plot, which helps us visualizing the distribution of a factor or categorical variable. Specifically, what we're going to look at here is the proportion of respondents in this survey that experienced violence from the international security forces. So we have here the outcome variable Afghan, where Afghan is the data frame, violent.x.isaf is the variable name. And so in order to create this bar plot in R, the first thing we're going to do is we are going to create a frequency table, which you've seen before. And if you remember from our previous video, we include the argument exclude equals null. This ultimately means that we're including missing values as an additional category in our table. Then we're including this prop.table command. This prop.table command turns the frequency table with raw counts into a proportion, into a table that shows the relative proportions in each category. Okay, and then all of this is then the input for our bar plot, which will visualize these proportions, right? We then have a couple of additional arguments. The names.arg provides the labels for the individual categories, which are no harm, harm, and non-response. So whether they experience harm or didn't experience harm. The main argument helps us setting the overall title of our plot, which here is civilian victimization by the ISAF. Then the label for our x-axis is response category, y-axis is proportion of the respondents, and then we specify the limits of our y-axis to range from 0 to 0.7. Okay. And if we execute this, the output will look like this. Oh, I have to move myself up here. Or maybe I'll move myself here. And what we see, of course, is the proportion for each response category, where about 60% of respondents did not experience harm by the ISAF. About a little bit less than 40% did so, and we have about 2% who refused to give an answer to this question. Okay. All right. So that's the first category of plots. Another kind of closely related category is called a histogram. A histogram helps us visualize the distribution of a continuous variable, right? So the bar plot helped us kind of visualize the distribution of a categorical variable, and now we're looking at a continuous variable, right? And so one way to kind of characterize this distribution of a continuous variable is to create bins along the range of the variable of interest, right? So if the variable ranges from 0 to 100 or something like that, we can create bins from 0 to 10, 10 to 20, 20 to 30, and so on, and then count the number of observations within each bin, and then plot basically the number of observations as the height of those bins. All right, and so usually with histograms, the way we kind of visualize this is by plotting the density, which is the proportion of observations in the bin width in a specific bin divided by the bin width. Okay, and R, in order to produce these plot, we use the hist command for histogram. For example, here we're looking at the distribution of age in our Afghan survey, Afghani survey. We include the option frequency equals false, so that we look at the density rather than the total frequency. We specify the limits of our y-axis. We provide an x-axis label, and we provide a title of our plot. And then the resulting plot looks like this. We have our age distribution with densities on the y-axis. Okay, and that gives us an idea of how this continuous variable is distributed. So what is the density, and why do we use density rather than ultimately raw frequencies? The density is helpful if we want to compare distributions, for example, from different surveys where the baseline of numbers is very different. Ultimately, it kind of puts everything on the same scale, right? The underlying idea of the density is related to kind of overall the idea of probability densities that we'll talk about a little bit later in the semester when we talk about probability distribution functions. But ultimately, the idea is that, of course, the area or the bin, the height of the bin, of course, is proportional to the number of observations in each bin, but the actual density value is kind of set up in such a way that all the areas of each of those blocks or of each of those bin sizes sums up to 1 or to 100, right? So that's why we kind of, usually it sums up to 1, right? So that means that the density is, of course, not equal to the percentage or the proportion of values, right? And that's something that is, very, very easy to kind of confuse. But it's important to emphasize that it's not equal to the percentage, right? And so by virtue of not being equal to the percentage, for example, what we can see is that densities can be larger than 1, which for a percentage or a proportion wouldn't be the case. The idea, though, is that the way you can think about it is that the area of all the bins, if you combine all the areas together, it sums up to 1, right? And that is a useful property for us if we want to compare different distributions, and also once we kind of think about underlying probabilities of cumulative densities and things like that, right? So when we use histograms, of course, we can make different decisions about how these bins, how wide these bins should be and things like that. And we can choose a lot of those or change a lot of those default settings, for example, by choosing the bin locations on our own. This can be done using the breaks argument in the hist command, or the n-class argument, which helps us set the number of bins, which can kind of help us with different distributions, or depending on what kind of level of precision we want to have, this can be helpful to kind of set larger or smaller bins, right? So for example, what we're going to look at here is now education years in our survey, and we're going to look at we're going to set up the bins, the breaks, such that they're ranging from minus 0.5 to 18.5 by 1, so that we basically have frequency or densities for each individual year of years of education, right? So if we look at that outcome, we then see a plot where we have years of education, and we have 1 bin for each year, and we see the density for no formal education at all, and then the distribution for higher levels of education. whenever we talk about distributions of continuous variables, oftentimes these variables are skewed, are not really distributed in a way that is easy to work with. And we'll talk later about what exactly that means or why that is the case. But in many cases, we want to, if we have distributions, for example, that are extremely skewed, like the example that we just saw, we might want to use a logarithmic function to kind of transform the underlying variable, right? So for example, with skewed variables like population or income, we can use the log function to kind of get the underlying distribution into a more normal shape ultimately. And this will help us, in some cases, will help us with our analysis later on, and we're going to look at examples of why that is the case and how we interpret also models that include logged variables, logged dependent or independent variables as well, right? But the key is just to give you an example. Here we're looking at the Afghan village population across this survey, right? And so if we look at the density of the population in thousands, we see this is a very highly skewed variable because a lot of the villages in those provinces were extremely small and just a few very large villages. So obviously that distribution is very skewed, and so ultimately when we're looking at models that want to include population size, we might want to use the log of the population, because the log of the population, distribution is actually much more normal, more less skewed, more normally distributed. All right. Another way to characterize the distribution of continuous variables is the box plot, which directly provides a lot of information about the distribution of a variable. Right. So here we have again the distribution of h. Rather than showing the histogram, we're kind of directly visualizing some key characteristics of that distribution in one single plot. Right. And there are a couple of key elements of a box plot. The first one is this large central bar, which indicates the median of the distribution. So 50% of values, of h values, are below that median, 50% are above. Then we have the interquartile range, which we talked about before. So that's where 50% of the observations lie between the upper quartile and the lower quartile, which is the 25% quartile and the 75% quartile. Then we have these whiskers, which basically range for up to 1.5 times the range of the interquartile range. And I mentioned this in one of the previous videos because that helps us identify outliers. All these individual points that are outside of this whisker they're outside of the 1.5 interquartile range from the lower and upper quartile, which classifies them as outliers potentially. Okay. So how do we create box plots in R? We can do that using the boxplot command, and importantly, we usually don't want to just look at one box plot for one variable, but we want to compare box plots we want to compare distributions of one variable across different groups, for example. So here what we're going to look at is education, the years of education by province. So we want to look at the education distribution across different provinces that are included in our in the survey. The data, of course, is the Afghan survey, and we set our title and our label for the y-axis. So the result of this this command can be seen here. Of course, we see different distributions for different plots, and we see, for example, here Helmand, one of the provinces that experienced a lot of violence has the lowest levels of education compared to more central, further north provinces that are located further north. Okay. Oops, that's not what I wanted to do. I wanted to move myself back over here, and so that's box plots. They can be extremely helpful if we want to compare distributions quickly across different categories, or the distributions of the same variable across different groups of respondents, for example. And so we'll use those a lot as well. Um, um, the idea of comparing distributions across different categories already kind of brings in this idea of ultimately looking at relationships between different variables. And so in the next video, I'm going to focus on summarizing bivariate relationships between two sets of continuous variables, both visually and using correlation coefficients.